Hi everybody, thanks for joining the webinar today. We'll get going in 1 minute here. Okay, I'm going to get going now. Thanks for joining us today. Our topic today is motor noise, and Anchong Stephen Liu will be our presenter. My name is Chris Cowan with Ozen Engineering, and I'm going to take a moment to introduce my company. Let me note here at the beginning that if anybody has any questions as we proceed through the webinar today, please feel free to type out your question in the questions toolbar of the GoToWebinar user interface that you should see, or to type it in the chat. So about Ozen Engineering, we're a company focused on simulation entirely. We use FEA, computational fluid dynamics, and low frequency and high frequency electromagnetics to solve multidisciplinary simulation problems. We are a certified elite Ansys channel partner, and most recently selected as the channel partner of the year for North and South America. As a channel partner, what that means is we sell Ansys software. We provide training to help software users use the tools successfully. Similarly, we provide technical support in case of problems. And we also provide engineering consulting services for companies who don't have the manpower or the software tools currently available. We work with the whole suite of Ansys software tools. Today, we're going to be focusing on Maxwell, low frequency electromagnetics, and mechanical, which are used in combination for motor noise. And you'll see that most of these software tools are, they work together on the Ansys platform to enable multiphysics solutions. We do these webinars every week or every 2 weeks. You can see on the right side here a list of recently completed webinars. You can find these all on our website, and you can see for I have the dates wrong here, sorry. These are in December. You can find the better dates on our website under training. Upcoming, we have 5G applications and Twin Builder for digital twin applications. Those are, 2 of those are in December. So please feel free to join us. If you want to get updates, our newsletter goes out every month that informs about upcoming trainings and webinars and general technical tips. From our website, ozeninc.com, under resources, you can go to the webinar library, and when you're there, you can pull up any of these previously recorded pardon me, webinars, or you can subscribe to our newsletter from there. One thing I'd like to tell you is that Ansys Cloud is now available. It's supported for electronics applications, including HFSS and Maxwell, and mechanical and FLUENT. The benefit here is one-click burst to the cloud. You can solve very large problems without owning very powerful compute equipment. The nice thing about it is that it's fully managed by Ansys. It works as a nice solution with the software, and this will enable you to really get better functionality of the software that you're working with. If you're interested in a trial, please let us know and we can help set you up with that. I'll tell you also that Ozen Engineering is hosting a technical conference in the year 2020, February 19th. This is going to be at the Computer History Museum in Mountain View. I'd like to invite all our participants here to attend. We're going to be focused on Ansys technical topics, specifically things like digital twin, FEA, CFD, additive manufacturing, 5G antennas, and Internet of Things. So you can contact us if we don't have the registration up yet, but if you're interested, contact us and we'll be happy to get you signed up for that. You can reach Ozen Engineering by email, info@ozeninc.com, call us directly, or find us on the web, and you can fill out a request form online. One other thing I'll add is that we're currently hiring for mechanical, electrical engineers, and we're always looking for people with experience in control systems for digital twin and embedded systems using SCADE, Ansys SCADE. So I'd like to introduce our presenter for the day, Anchong Stephen Liu, who has earned a BS in electrical engineering from the University of California at Santa Barbara. For our customers who work with electronics applications, you probably have spoken with him for technical support requests, and I will send that over to him right now. Thanks for your attention.
All right. Thank you, Chris, for the introduction. Okay. So today's topic is motor noise. In other words, it's another topic for another title for this is really Ansys Solution for electric machine NVH. NVH stands for noise, vibration, and harness. So in the industry, noise is a hot topic for electric machines, and competing requirements such as weight and cost reduction are causing engineering challenges that, if unaddressed, can have an impact on customer satisfaction and product acceptance. So using the Ansys suite of tools will provide engineering guidance on how to holistically address motor noise. In other words, please consider excuse me, something was playing in the background. So in other words, please consider the multiphysics approach that will show in the following presentation as an example, and you can probably benefit from the same simulation-driven noise reduction that other Ansys customers have already achieved. Electric machine NVH, what and why? So noise, as we talked before, NVH stands for noise, vibration, and harshness. Is the common nomenclature for audible sound between 20 hertz to 20 kHz. The forces causing these vibrations can come from many sources. For electric machines, these may be magnetic forces that act to turn the rotor shaft, or they could be part of the larger drive system, such as from the bearings and or the gears. So a lot of the sources, and one of many requirements one is for system performance, one is for packaging, one is for durability, and NVH is considered, and lastly as well the cost. So if we look from a diagram perspective, so from vehicle, there are three very possible sources of noise. One is from the powertrain, one is from the road feedback, and the other one would be wind noise. So it affects product quality, real and perceived. So poor NVH would essentially cause a low quality. So the principles applied here can be used in many applications and with many electric machine types. So not just in the automotive, in the electric vehicle industry, but also in various industries. The resulting information shows how forces are transferred through the system and then heard by a customer. So other than the car industry, the traction in the drivetrain, pumps, fans, and of course we talk about HV hybrid vehicles. Uh, it's also possible in the lifts, in the robotics, medical devices, generators, and the turbo machinery, and as well as some of the consumer devices. So, for example, on the right we have a CAD of an electric machine. So we see the rotation direction, a roller. There's a roller torque, and then load torque on the output shaft, and then the gear excitations. So in a system like this, there's vibrations in between the gearboxes, and when we talk about electric machines, there's a lot of we Ansys is aware that there's a lot of different electric machine types from permanent magnets, AC, BLDC, pulse width PWM, induction machine, switched reluctance machine, synchronous reluctance machine, and so on and so on. There's a lot of machines needs to be addressed in order for Ansys to have a uh, full comprehensive portfolio or templates for those machines in order uh, to simulate. So the Ansys solution provides finite element analysis, simulation, and expertise in all areas of noise contribution. So this presentation highlights the main steps from calculation of excitation forces, structural vibration, and acoustics. This is all contained within the Ansys Workbench platform. So some of the advantages of using Ansys solution for NVH would be, it's highly accurate, it's detailed physics, which means it's physics-based simulation. It could also be flexible and easy to generate the models. Uh, and we all and by using Ansys, you're using one common platform. We call it Workbench. So this one common platform gives you some of the benefits, such as automated file transfer. Once you have a geometry ready, you can this geometry is this geometry is shared between all physics, so you don't have to reading and transfer the geometry. Uh, it can includes all noise sources, and there's also you can also do a optimization on the best possible design, not just a better design, but the best possible design. So yep, that would be the some of the advantages in summary. Um, so the diagram on the top is the workbench workflow that you will actually see when you're working with the project. So each block represents a physics. From the very far left side is just the geometry alone. So that's the motor geometry. The G block is the Maxwell block that takes care of the electromagnetic side of the machine. Then you can send this to the third block. H block is a fluent block that it's not addressed. So this physics is not very much addressed in the presentation, but what I know is that um, you can work on the fluid physics with if it's turbo machinery, there's probably some fluid physics you want to emphasize, as well as you can use Fluent to do a fluid structure interaction analysis, either one way or two way FSI. And the last two, one is static structural of the electric machine, and then the very last block is a harmonic response. The the diagram, the lower diagram is a kind of like a schematic diagram. So OptiSLAN is a optimization tool that's I believe recently has been acquired by Ansys that helps you to optimize your design uh, to as we said, the best possible design. Design Modeler is really just the CAD tool of Ansys. We also have SpaceClink that would probably do the same. Design Modeler is a little bit more powerful in the electrical machine turbo machinery in terms as opposed to SpaceClink does. Then from Design Modeler, you can send the geometry to either Maxwell on the top, that's for electromagnetics, or to mechanical. And then optometrics and parametrics simply means that you can have parameters in your design that, oops, there's a question I just saw. Is the fluid structure interaction necessary in the image or just a fluid or heat transfer? So the question is the fluid structure interaction necessary in the NVH analysis or just a fluent or heat transfer? I don't think that's necessary. The fluid, the FSI. I only mention it because I know it's a capability and it is working pretty well, but no, it is not necessary. To answer Roberto's question. Okay, I'll carry on. So now we get to the steps of the solutions. So we take a look at the solutions for each step of this NVH process. So the first is the magnetic field solution. So now we're seeing a section of a 2D view of a section of the electric machine. On a from this, so this has the stator structure and the stator uh, just have the stator, actuator, and the tooth of the machine. And from this 2D model alone, you can get a tangential force on the teeth. That's a time versus force uh, plot. So so we talk about there are so basically there are four steps in the NVH process. We talk about a magnetic field solution, then the second would be the modal vibration, acoustic, and then VR experience. So we're splitting the process into steps, with the understanding that the approach is holistic in terms of the vibrating structural system. So as we said, the steps are presented here on the slides. There are four steps. The magnetic solution is to determine the radial, tangential, and axial forces associated with the machine performance. The second, the structural simulation part. Uh, um, in the so the second step is structural is for modal and vibration. So the structural simulation and design incorporating all forces basically. Then the third would be acoustic representations of the radiating vibrational noise. And then the fourth would be the experience of the acoustic resulting audio format. So uh, we can uh, we can basically replicate exact what you are going to be hearing from the electric machine from our software, basically. So for the magnetic FEA forces, the first step can be calculated, can be used to calculate magnetic forces. We've been talking about this. So these can be regular forces on each of the discrete stator teeth, or these can be um, these can be due to high frequency drive switching, or these could be due to unbalanced magnetic pull. All of these can be calculated along with magnetic performance and efficiency from the FEA simulation. Usually, this is calculated in the time domain for electric machines and is converted into frequency domain representation. The output are forces, radial, tangential, axial. These forces are applied as inputs to the next step for the structural simulation. So we're looking at a animation, time domain animation that tells you the speed is 3,000 RPM and gives you the position of the magnetic force, the edge force density, basically, on the T's. Then we can use those forces as inputs when we go to the structural simulation. Plots can be drawn as well for the radial forces on the T's and the tangential forces on the T's. We can also plot FFT tangential forces on the T's. So essentially, it could be it could either be 2D or 3D, periodic or full. Okay. So for a specific machine model in Maxwell or Simplorer, so here we have an example of a machine that is connected to an electrical drive with SPWM, a step piecewise module. It can be modeled in either. So this SPWM can be implemented either through a external circuit tool in Maxwell or in Simplorer with it can that enables a lot more advanced controls. So either one can be connected to a harmonic force structural analysis. The machine. So on the in the center we have a 2D model of the machine. Right next to it on the right is the external circuit in Maxwell. So as you can see on the left, there's a bunch of step inverters, and then the machine, I believe, is represented on the right. And then on the lower left, we have a circuit schematic for external circuit schematic in Simplorer. So on the left side of that schematic, it's identical to that in Maxwell, but on the right side, we can see that the resistors and inductors that represents the electric that represents the machine is replaced by a block that's a Maxwell block, Maxwell component block in Simplorer. So it's a coupling. It's really a coupling technique in Simplorer. So nothing much more different between the two at this point, but Simplorer does give you a lot more control abilities, or in terms of more functions, more functional blocks, and more templates. So the machine we are looking at, the machine that used in this study is a 4-pole 1500 RPM 220 volt DC bus, interior PM permanent magnet motor created from RNM Expert and Maxwell UDPs. So this model is created in RNM Expert. For those of you that doesn't know what RNM Expert is, for those of you who doesn't know, RNM Expert is it is a design tool that gives you a lot of templates, templates for electron machines, and you can create models you can create models with there's a lot of different parameters you can change in those templates, and you can from there you can easily generate a model instead of drawing from the scratch. So either using Maxwell circuit or co-simulations Maxwell with Simplorer is the way to go in this case. So for Maxwell force calculation details, so we can calculate either edge force density or Maxwell stress. So the edge force density is on a magnetic objects. It's a virtual work method. Maxwell stress tensor density it's on arcs within the air gap. Then after the Maxwell solution has come out, we can couple this with mechanical in Workbench. So Maxwell calculates the object force and moment force and moment on each tooth object. So then the force is integration of the density, and then so the definition is that force is integration of the density. Moment is next order of accuracy that would cause extra stress due to twisting of the tooth tip. Object-based force mapping often works well due to discrete gaps for each tooth. It's good for 2D magnetic to 3D structural coupling. No force density distribution mapping required, which reduces the mesh requirements. It will also be easy to replicate from one motor pool to the full model. So that's why we would usually start with a 2D model, then expand it to the entire 3D model. So all of this coupling enabled directly in the interface automatically applies real and imaginary forces and moments in Harmonic. So in Ansys, so this workflow can use either object-based or element-based. So the harmonic force calculation offers flexibility in the magnetic FEA model and in the force transfer method. So this is ideal for different types of electric machines with 3D effects. So as we said, so the structural analysis part, the step 2 can take either 2D or 3D Maxwell model, and it can either take full or fractional of the pole pair of the Maxwell model. It can take either object-based or element-based mapping as well. For object-based, it means just a stator tooth. If it's element-based, then that would be the entire stator. So the 3D eccentric models take longer to solve, but using HPC, that would make it a lot faster. Speed sweep starting with version 2019 R1, we can do a speed sweep with multiple RPM in Maxwell. So based on the single RPM workflow, that supports both object and element-based mapping. So that's what the first that's what the first plot is telling you. So you can check the stator for force dependent to switch between object or element based mapping. For the second one, it gives you it gives you the Maxwell transient design provide. So essentially it provides the force density on different frequencies in RPM. So you can check the consider mechanical transient to enable that. Then it's also available for scaling then it's also available for scaling the source frequency, uh, and then scaling the end time and the time step, then adding the parametric study, and then send that to Design Explorer, which is the optimization tool, which is embedded parametric analysis, and it can save fields and meshes on each time step. So after setting these, the harmonic response consumes force densities of different frequencies, and then generates ERP map in the structural harmonic results. So we talk about how Maxwell is being how we go from step 1 from Maxwell to step 2 in structural. So now we get into step 2. The second step is to design and analyze the structural response of the system. So these analyses can include modal free vibration simulations to determine the resonant frequencies, coupling, and mode shapes. This can also include calculation of structural forcing functions, such as gear noise. Then all these forces and the magnetic forces can be used as inputs into a forced harmonic vibration analysis to calculate the absolute magnitudes of the vibrations. So essentially, these structural vibrations can be used in a ERP calculation, or acoustic or fatigue, and or as well optimization analysis. So these are all incorporated. These are all incorporated into the workbench environment uh, for either your CAD or mesh sharing, this design studies, or optimization. So there are some CAE challenges uh, for material properties, especially for laminated steel. It is important, but often unknown. Um, so Ansys Workbench or the Design Explorer provide a integrated workflow to calibrate the material property based on your frequency test. So in the engineering data, you can modify and calibrate your material property. So just a couple of diagrams to illustrate that the connections, joints, and the contacts, how they're being defined and then how they are being taken care of. Oh, I just saw another question from Roberto. The triangular wave for the PWM, what frequency it has? We can go back to the slides, but he was also asking if it can simulate 10K hertz, for example. I think that is for sure. So it goes from 20 hertz to 20K hertz at least. So really the frequency is you can define a frequency in the software based on your demand. And then we also have the combined solution for both motor whine and the gear whine. So a single platform for motor noise and gear whine noise simulation. So the steps would be on the left, so running a static analysis on a gear pair to evaluate its flexibility. Then we would evaluate the manual contact stiffness of such a gear pair. Then we would model a transient analysis with rigid gears and a manual contact. Output the transmission error for a given input speed. So on the left, on the first step, where the very first step is loading the teeth, then The second step, we're just trying to get the deformation calculation. And lastly is implicit MBD solution. MBD stands for motion body dynamic. Some of the modeling details, we have fixity on these certain points, both pretension and static, and rot Z fixity on the shafts, so it's rotating around the Z axis. That's for the structure. For the harmonic, there are loads import from Maxwell 3D on the stator teeth, and then the gear excitation for spectrum. And then lastly, we have a appropriate reactive momentum. Moment is applied on output shaft. And we can do a modal and harmonic results. For the modal, we can calculate different modes. Here we have the mode 14, mode number 14, and the mode number 21. And for the harmonic, we have we can show you the total deformation under different frequency. On the top, it's 950 hertz. On the lower side is 1400 hertz. We also we have Ansys from 2019 R1. We have also started to introduce this automated waterfall based on the multiple RPM. So it is important to analyze the acoustic signature across multiple RPM for electric machine design. So we have here, we can have a waterfall diagram. That's our frequency versus RPM. So as you go along the plot, the higher the frequency, then the higher the pitch is of the noise. So as we said, after the second step, we'll go to the third step, which is acoustic and equivalent radiated power. That's what the ERP will stand for. So the force structural analysis procedure produces the surface vibration of the structure. Then, these surface vibrations are what cause the pressure change and sound propagation in air. Then this ERP is the equivalent what ERP stands for is equivalent radiated power, which is a structural approximation for the radiated noise based only on the surface velocity. So no acoustic simulation required for the single approximated quantity. The full acoustic simulation gives accurate results on every representing pressure and SPL as well as far field results. So this would share the same interface as the workbench mechanical GUI, and it was integrated into the building setup since last year. So on the top, we have a surface velocity import from the structure harmonic, and then we have air doming around the power train. Then we can calculate the ERP versus frequency and RPM. And we have SPL, which is sound pressure level, and also far field SPL versus angle theta. So the last step will be Acoustic Experience. That will be a run-up model to ERP audio. So we have the ERP waterfall diagram. Then we can listen to this through our VR experience sound dimension. So we can listen to the computed ERP. I'm not sure if this can be, you guys can hear this. So as we go, so in this diagram, the waterfall has been rotated So so that x-axis is the RPM, and then the y-axis is the frequency. So as we go through the RPM, as the RPM goes higher, then the higher the frequency, so that the higher the pitch is of the noise. And then on the lower is the waterfall sound synthesis synthesis uh, of the of this waterfall diagram. So just a conclusion of this multi-physics workflow. So we started with electromagnetic field, then structural dynamics, then lastly we go to acoustic field, electromagnetics, modal and harmonic response, and then lastly is the harmonic acoustic. So for single RPM, we can use the Maxwell 3D. If we want to do a multiple RPM, then we probably want to go with the Maxwell 2D. So also you can either so you can either stop with the ERP at the structural harmonic, or you can continue to acoustic to get the audio representation. So another thing to note here is in 2019 R1, we're in 2019 R3 version right now. So this was introduced in 2019 R1. So the element-based coupling takes a really long time with the modal harmonic approach. So either we would use object-based coupling with modal and harmonic responses, or use a full harmonic solve. So this is kind of a limitation in terms of the computational power. So this will be improved in a later version. So this would be all. After this conclusion, this will be all for my webinar today. I see another question, a couple more questions. First is, why in the waterfall there was no visible frequency at the PWM frequency higher than 1 kHz? Oh, and also, but the H-mean in Simplorer would limit the triangular wave frequency, isn't it? Uh, the waterfall question I can't answer. I can follow up with that. For the H mean, you are correct. So H mean, you're talking about the setup at the minimum time step of the setup. So yes, that would limit the triangular wave frequency. So this is what I've been finding that if your frequency is really high there, then your H mean needs to be uh, even small. So you have to have a really smaller time step to address those um, really high frequency time blocks or functional blocks. Where can we find examples to understand involved details? I don't have I don't have the exact project of this. Um, shoot us an email on, if you have the need for the examples. Shoot us an email at support@ozeninc.com, and I will coordinate that. There's what is that? There was a hand up. Can you get student version of Maxwell 19? Um, we don't deal with, so we are Ansys channel partner, but unfortunately we don't deal with academic licenses. So the answer is yes, I believe so, but without knowing your current status, I would say just contact Ansys direct generally and see what they have to say about academic licensing. Uh, okay. Okay. Would Okay. If that's all the questions we have for today, then have okay, two more questions. Okay, a couple more questions. How do we incorporate real life test data into the simulation to determine where to focus on in NVH challenges? So this workflow is purely a simulation. How do we incorporate real life data? Um, that really depends on what kind of real life data you're talking about. If it's uh, if it's the ERP, then I guess we can just compare the different plots. Yeah, I guess it really depends on what kind of real life data. Speed, vibration, clutch. Yeah, the simple answer would be just comparing the results with your test data. And then if there's any discrepancies, then that's probably where more focus needs to be put on. Can I get the complete tutorials for doing acoustic analysis of motor? Uh, um, I'll have to follow up that. Send an email to support@ozeninc.com. I'll need to look for some materials for you. I'm not sure if there's a complete, like a thorough tutorial, but some there should be some. So I'll need to look for it. Have I tried running PWM at 10K hertz? Not that I remember, to be honest. I never, because this is pretty detailed, so I've never used specifically PWM at 10K hertz. So this is what I would say. So it seems Roberto. So it seems that this is something you really care about. And so set up for 10K hertz, and then for HMing, set it for how much is 10K. So probably set HMing to um, 1 microsecond or 10 microsecond. I think that should give you a beautiful triangular PWM PWM plot. That's what I would suggest. 3K hertz. Okay. Okay. That sounds okay with me. But if so, my experience is that I've run a couple of Simplorer projects, and what I noticed is that this um, time step is this time step is somewhat crucial to your simulation. And not only the H mean, but the H max is also important. So if you have your H mean that's really small, but your H max is not that small enough, so the doing the simulation at each time step, it would, sorry, not doing it, not so doing the simulation, the time step would vary based on your setup and your model. So say your HME is 50 microseconds and your H max is say 100 microseconds. So sometimes the time step would be 75 microseconds. So it would take a middle point. You know what I'm saying, in between the HME and the H max. So that's something you want to pay attention to. Okay, there's a lot of questions. That's a good sign. Okay, so thanks all for your attention today. This would be the end of today's webinar. Uh, as we said before, if you have any questions, feel free to call us in or send emails to support@ozeninc.com. We'll be happy to get back to you. All right. Bye. Have a nice day. Thank you, everyone.